Welcome to April 1st, Kitchen Table Chemistry. We're going to take a look at some stuff today, and I'm going to try and record myself. Most of this is a review of what I assigned for you yesterday and a few thoughts for today. So at the end of today, we want to be able to describe factors that affect rates of reaction and relative rates of reaction. So the 5 factors that affect reaction rates. First of all, the nature of the reactants themselves. Their atomic radii, their ionization energy, valence electrons, these types of things that will influence how fast things react. And if you think of as an example, sodium versus copper. Sodium with 1 valence electron and a very large atomic radii, very active, going to react very fast when compared with something much more stable like copper. So the nature of the reactant is a huge factor. The concentration. What is the molarity of the reactant being used? 6 molarity versus 1 molarity. Obviously, with 6 molarity, you have more of the reactant. You're going to get more collisions. And whenever we're looking at a reaction, we're thinking of how many collisions can we get. The ability of the reactant to come into contact with each other, area of contact. In other words, is it a gas or a vapor or is it solid? In general, gases will react faster because you have much more surface area, as will anything in solution. Solids will react much more slowly because of that limited amount of surface area. Temperature, which is the kinetic energy of the particles, again, will influence their speed and their ability to collide with enough energy for a reaction to take place. And lastly, a catalyst. Is a catalyst present? If it's present, it is going to reduce the amount of energy needed for the reaction to take place. A catalyst, a substance that lowers the activation energy of a reaction, is something that we always want to be careful of. But in kinetics here, it's going to affect the rate, but it's either going to be there or not there. When we talk about things reacting, take a look at this diagram where we have potassium reacting with methyl iodide. The potassium ion in the orange has to collide with the purple methyl iodide. If it collides directly with the purple iodide, then we get a reaction producing potassium iodide and a methyl ion. If the potassium connects with the methane end, then no product is formed because that geometry will not allow the reaction to take place. So in a collision, the geometry is important. In order for a collision to be effective, we have to have this idea of things colliding in the correct geometry. Here we have nitrogen monoxide combining with ozone. If the, doesn't matter which end of the nitrogen monoxide it is, if it hits the central oxygen atom of the ozone, which is O3, we get no reaction at all. But if the nitrogen monoxide hits one of the end oxygens on the ozone, then we get a reaction, an effective collision, we get nitrogen dioxide and oxygen produced. So that idea of an effective collision, it has to have effective geometry. Now on this slide, I've kind of put the two things together here. The must-haves for an effective collision. We've got to have the correct geometry, and the steric geometry, sometimes called steric geometry, but the correct geometry or the orientation of the molecule, and enough activation energy for the reaction to take place. This is a minimum amount or a threshold level of energy that's needed for the reaction to occur. Both of these things must be present in order for the reaction to happen. Looking at a catalyst effect, here we have two reactions. One is in a blue line, the other in a red line. Energy is shown on the y-axis and time on the x-axis. The uncatalyzed reaction simply takes more energy, more activation energy in order to occur. The catalyzed reaction will occur at a lower energy level and therefore is perhaps going to occur more quickly and is more likely to happen. When we think about kinetics, we're thinking about things progressing from reactant to product. We're going to start at time 0 with nothing but reactant, and then we're going to end when our reaction ends with mostly product at that point in time, where the reaction will have proceeded to wherever it ends. So this is how things are going to go. We're primarily going to be concerned with the concentration of the reactants because when we start this, there will be no products. Again, shown on this diagram, where we have the molecules of A, which are the reactant, and then the molecules of B, which are the product. So we start with A and no B at all, and then as we go, the concentration of A decreases, while the concentration of B increases. And again, this is just how a reaction progresses. Now, here we have relative rates of reaction, and this is going to depend on the coefficients from the balanced reaction, and this is today's idea. So if we look at this reaction with 2 butane plus 13 oxygen yielding 8 carbon dioxide and 10 water, the ratio between the butane and the oxygen is 2 to 13. So for every 2 moles of butane, you'll need 13 moles of oxygen. In this case here, the given is 0.20 moles of butane, and you'll need then to set up a stoichiometric ratio with 13 moles of oxygen over 2 moles of butane. That will allow you to cross out this. Now, I've tried to make a video showing this, and I'm not sure if I can get it to upload or work properly, but I will eventually. This has been a learning curve for me, for certain. But to solve this, and I've assigned you 3 questions out of the text in doing so, you're simply going to need to set up a mole coefficient ratio. You'll have the ratio of one, or I'm sorry, the concentration of one thing and the rate at which it's decreasing. So the concentration, 0.20 molarity per second, is the decreasing concentration of the butane. And because you have the coefficients, you can simply set up that mole coefficient ratio, which in this case, to solve for oxygen, would be 13 over 2. I'll let you take a look at these. And I'm going to link at least one other video here in today's assignment for you to take a look at. The questions I'd like you to attempt from the text today are on page 563. They're questions 530, 350, 351, and 352. Most likely the easiest way to do this is on paper, and then to just send me a picture or link it to your assignment somehow, and that I think it could be time consuming to try to put in as text. And that, but you'll let me know as we go along what works better for you as a student. So again, today's idea, relative rates of reaction, and I hope you've enjoyed this first look at things. As always, let me know if you've got any questions or concerns, and please send me any sort of suggestions or improvements that you think I could make. Thank you, and I hope you're doing really well.